In the last video, we found the electric field from a line of charge. Now we're going to take that line and bend it into a curved arc length. It's still a one-dimensional charge distribution. The charge is still uniformly distributed, but the charge is distributed over a curved arc length, and we're finding the electric field at the center of curvature. So the process is the same. We're going to pick a little tiny element of the charge and call that dq. That dq is so small, we can treat it like a point charge. So the amount of electric field it produces, and because the charge is negative, the electric field will point toward dq, and we'll call that dE. So we'll treat it like a point charge. The electric field produced by a point charge, kq over r squared. The electric field at the origin due to dq is going to be our constant k times the amount of charge we have that's producing the electric field, that's dq, over the distance between dq and our point of interest squared, k dq over r squared. We want to add up all the contributions from every little dq along our line of charge. But the electric field is a vector quantity. So we can't just add them up because each little dq, the one that I just drew here in red, produces an electric field that I drew pointing up and to the right. But there's one down here that produces an electric field this way. And there's a dq over here that produces an electric field this way. And we have to add them all up. And we have to break them into components first because you can only add vectors in the same orientation. We must use vector components. So we're going to find dE in the x direction, and we're going to find dE in the y direction. dE in the x direction will point like that. And in the y direction, we need to pick an angle in order to break up dE into its x and y components. And there's two obvious angles there we can pick. We can pick the angle with the x-axis, or we can pick the angle with the y-axis. I'll use blue for this angle. I'll call that theta. Or we could pick this angle up here. I'll use a green color, and I'll call that phi. If we use theta, then the x component has a cosine theta in it, and the y component has a sine theta. And if we use phi, it's the other way around. The x component has a sine, and the y component has the cosine. Either way, doesn't matter. We should all get the same answer in the end because what's going to happen is our limits of integration will be different depending on which angle we choose. So in the end, we will all get the same answer. In fact, why don't we do this? Why don't we do it both ways using both angles? First, let's use theta, the angle between dE and the x-axis. If we use theta, dE will be k dq over r squared times the cosine of theta, and the y component will be k dq over r squared sine of theta. Remember, here's our electric field vector. And we want the x component, so we would use cosine of theta. And for the y component, we would use the hypotenuse times the sine of theta. So here's our dE, And here's our sine theta, and that gives us our y component. We have a dq, we have a theta, we have an r. We've got to get all of this in terms of one variable that we can integrate over, because this is a one-dimensional charge distribution. We should have a single integral. Let's start with dq, because that tells us what our variable is that we're integrating over. In this case, dq is going to be our charge density multiplied by our length element, lambda ds. Because we have a uniform density, lambda is a constant, and our ds is an arc length along this path. Our ds is this arc length, and that arc length is equal to the radius times the angle, and the angle is going to be d theta. The reason we end up with that is that our arc length here, if subtends such a small angle, we call that d theta. Theta is the angle toward dq, but dq actually has a tiny bit of width to it, a tiny length to it, so it subtends an angle d theta. And if you're in radians, the arc length is equal to the radius times the angle, or in our case, ds is r d theta, if you're in radians. So ds becomes r d theta. R, on a circular arc length, where our point of interest is the center of curvature, is a constant. And this tells me my variable that I'm integrating over is going to be theta. So I want to get everything in terms of theta. I'm not going to change this cosine theta into something in terms of x and y, because the dq tells me that I want everything in terms of theta. As soon as I get my dq in terms of d theta, as I have here, that tells me that's the variable I'm integrating over. Turn everything else into theta. If I have a sine theta or a cosine theta, leave it that way. If I have an r that depends on theta, convert it into theta. But in this case, it doesn't. It's constant. We'll just leave it the way it is. So I know my variable I'm looking for is theta, and r is a constant. So let's set this up. And now would be a good time to stop and think about our answer for a minute. What do we expect the answer to be? Do we know one of these already? Our charge distribution is symmetric. That tells us that all the y components will cancel out. E sub y is going to be 0, and we're only going to be left with an x component. And because this charge is negative, the x component will point in the positive direction, the positive x direction to the right. So I could write E sub y is 0 by symmetry right here. If this was an exam, that's what I would do. But if I'm practicing, I'm going to solve and make sure I get 0. So we'll do that. First, let's take a look at the x direction. We're going to integrate. That turns our dE sub x into E sub x. When we add up all the contributions from all the little dq's, we have some constants here, k, lambda, and we end up with a 1 over r. We have an r over r squared, becomes a 1 over r. And then we have the integral of cosine theta, d theta, and we have to get our limits right. So let's take a look at that. Theta is measured from the positive x-axis. That means that our charge distribution, we've got charges all the way down here, all the way up until we get to this point at the top. So the charges are located everywhere from minus pi over 2 through 0 and up to positive pi over 2. As these charges vary along the line, the angle between the x-axis and the line that connects that charge to the origin changes from negative pi over 2 to positive pi over 2 if we're calling the x-axis 0, which we are in this case. But we don't have to do that. In the next case, I'll use the other angle here, and you'll see that the limits of integration change. Forget about some overall rule that the positive x-axis is theta equals 0. That is not the way this works in physics. You pick the angle that makes sense, and you define your origin and you define your 0 for the angle. So in this case, we happen to pick the positive x-axis with 0 like you're used to doing in math class. But in the next case, we won't do that. Our limits of integration, minus pi over 2 to plus pi over 2. Integral of cosine is sine. And this just becomes 1 minus a negative 1, or 2. 2 times k lambda over r. So let's put in what lambda is. Lambda is the total charge over the total length because it's a uniform charge distribution. And I always like to use the magnitude of the charge here and then assign the direction later. This integral does not give you the direction of the electric field. You have to figure that out. So let's use the absolute value of the charge and not worry about that now, and then we'll assign the direction later. So in this case, R is not given, but L is. L is given and Q is given. And we know we can write R as L over pi because it's half of a circle. So we can come down here and we can plug in some numbers and we get 2.16 times 10 to the 7th newtons per coulomb. The units for electric field, newtons per coulomb. Now that's the magnitude of the electric field. We need the direction. This is negative charge. So the electric field points toward the negative charge, which means it points in the positive x direction, or the positive I hat direction if we're using unit vector notation. Positive. Don't fall into the trap of putting a negative q in there and then saying this is in the negative direction. The integral does not give you the direction, it only gives you the magnitude. You have to figure out the direction yourself. Let's do the y direction real quickly just to make sure we get 0. In fact, you should pause the video and do it yourself. If you get stuck, come back. I'm going to set it up right now. This time we have an integral of sine theta d theta. our limits are the same, minus pi over 2 to plus pi over 2. And when you integrate the sign, you get negative cosine. Integrated from pi over 2 to negative pi over 2 gives you 0. Maybe I should write that one more step. Minus cosine theta from minus pi over 2 to plus pi over 2 gives us 0, which is what we expected. What I want you to do now is go back and do this problem again, but use the angle with the y-axis. Use phi and see if you can set that up and get the exact same answers. So we follow the same thought process through the problem. We pick a little chunk dq. We say that it produces some small amount of electric field, k times the charge, which is dq, over the distance squared, the distance between dq and our point of interest, which is the origin in this case. Now we want to add them up. We can't do that until we take components, till we break this into its component form. So dE in the x direction is going to be dE times the sine of phi. Let's go back and check, make sure I got that right. Here's our angle. The x component is the opposite side, so it would be the sine of that angle times the hypotenuse. And the y component is the adjacent side, so it would be the cosine theta times the hypotenuse. And I know dE is k dq over r squared. And I start plugging in things I know. I always start with dq. And I know that dq is lambda r d phi. R is constant, lambda and k are constants. The only variable I have is my angle, and I can just leave it the way it is. So I get, integrating both sides, my x component is k, lambda over r, the integral of sine phi d phi. Now, the limits of integration are different this time. There's a charge way up here at the top, and when I draw a line pointing toward it, what angle does that line make with the y-axis? 0 degrees. So I'm starting at 0 degrees, and as I move around to the other end, my angle is increasing. It goes through 90 degrees, and then it goes all the way down to 180. So up here I'm at 0 degrees. The charge over here would be at pi over 2, and the charge down here is at pi. So my angle phi is sweeping between 0 and pi. And that gives me a minus cosine evaluated from 0 to pi, which is 2. So I get the same answer I got previously. And the direction, of course, you'd use absolute values for your charge, and it would be in the plus x hat direction. Going through the y direction, you get the same thing. You end up with an E sub y is k lambda over r, integral of cosine phi from 0 to pi, and that gives you sine, which is 0. It all works out the same if you get your limits correct. So define an angle and how you're measuring that angle, and then look and see what angle do you have to cover all the charge. And forget about some old definition somebody told you way back in math class that the 0 has to be the x-axis. You make 0 whatever makes sense for the problem.